We're going to go ahead and look at comparing two proportions. And one of the ways we can compare them is by creating a confidence interval. But before we do that, develop the method to do that, we're going to go ahead and look at a cute little cartoon. So there are statistics which are mostly harmless. See the normal distribution here. Statistics that are dangerously misleading. And statistics which exactly match reality. We have a sense of humor in statistics. All right, so we're going to do this example. Mrs. Overman took attendance on Wednesday and marked 76 students present out of her total 86 students on A Day. On Friday, she marked 72 students present. She says both samples are representative of the typical Wednesday and Friday. How can she compare the attendance rate on both of those days? Well, first of all, the attendance rate would be the students that are present. And for Wednesday, that was 88.4% of students, or 0.884. On Friday, it was 72 over 86, or 83.7%. Typically, we would say how much higher or lower one measure was compared to another. So if we're comparing them, so we really want to calculate the difference. Now, if I'm going to compare the difference, recall from random variables that if the difference is y minus x, in this case Wednesday minus Friday, then the mean of the differences is the mean for Wednesday minus the mean for Friday. But I only have these, and these are point estimates based on the samples, so I'll use those, proportion 1 minus proportion 2. So my point estimate, I'm going to subtract those two proportions, and I get a difference of 0.047, or about 5%. Now, 4.7 is not the only possible value for the difference. So I know that there's some variability in there. We need to consider the sampling distribution. Now, when I'm subtracting two independent random variables that have approximately normal distributions, the difference will also have an approximately normal distribution. So we just need to confirm that both proportions are independent and meet the conditions for a normal distribution. Recall that the three conditions we checked, there's a large count condition, which I've also seen as success failure condition or large sample condition. Confirm that n times p is greater than 10 and n times q is greater than 10. But you've got to do it for both samples. So now I'm saying n1p1, n1q1, n2p2, and n2q2. So do all those products, or if you just have the successes and failures, compare those to 10. We also have the random condition, and the samples need to be representative. So this can be satisfied if you're told the sample is representative, period, or that it is random. There's also the 10% condition. The sample size must be less than 10% of the population, or it affects the independence of the trials. Now let's go ahead and check conditions for both attendance samples. So the first condition is the large count condition. And Wednesday, I had 76 successes. 76 kids showed up, but I had 10 failures. 10 kids didn't show up. But both of these values are greater than or equal to 10, so the condition's met for the Wednesday sample. For the Friday sample, successes are 72 and failures are 14. Both are greater than or equal to 10. For randomness, I'm going to tell you they're both representative. And if I tell you that, you accept it. All right. In terms of if the problem says it, you accept it. And then finally, the 10% condition. We can argue that we replace attendance each day, so we don't have to worry about the 10% condition. I'm not really using up more than 10% of my sample. There are multiple ways. You could say, oh, one Wednesday is less definitely than 10% of all the possible attendance records that I take over the course of a year. Either way, we have met the 10% condition. So once we confirm conditions are met, we can use the properties of a random variable to determine the standard error. Going again back to random variables, if the difference is y minus x, then the standard deviation squared, or the variance for the difference, is going to be the variance for y squared plus the variance for x squared. Remember, even when you subtract here, we do not do that for variance. We increase spread when we combine variables. Now recall that for proportions, the standard error for a proportion is the p times 1 minus p over n. And that's like the standard deviation. So SE means it's from a sample. I should really have little hats there. And then if I go ahead and substitute that in, I'm going to take this piece and substitute it in there for the Wednesday sample, and this piece and substitute it in for the Friday sample, or sample 1 and sample 2 in general. And when I square it, I end up getting rid of the square root, so it looks like I have just this piece. But that's the standard error squared. So the actual standard error is to take the square root of the whole thing. So if I take the square root of this, I get that. So now we know how to calculate the point estimate for the difference and the standard error for the sample. So once we've done that, we can do a 2-sample z interval for P1 minus P2. So it's whatever this point estimate is for the difference, plus or minus your critical value, and that new formula for our standard error. Remember, the critical value is calculated the same way as before, and the steps for the confidence interval in terms of determining the critical value are the same.